What is the best thing about Switzerland? I don't know, but their flag is a big plus. If you didn't get that joke, you should Google the flag of Switzerland. Everybody knows that the best joke is one in which you learn something, so you're welcome. Today we are finally going to get to integration, or what is also called the antiderivative. Not the enemy of derivatives. I like to think of it as the anti-hero of derivatives. It is going in the opposite direction, kind of. Not kind of, it is. We're going in the opposite direction. We are not done with derivatives. We will still do plenty with them. In fact, this is chapter 4, and then in chapter 5, we will go back and do everything that we've done with derivatives with transcendental functions. So we'll see our logarithms and our exponential functions come back into play and see how they would look if we're taking the derivatives and integrals there. So you'll get some of the same derivative concepts again in chapter 5 with new types of functions. Okay, so starting with the basics, how do we find what is called an antiderivative, or indefinite integration is what we're going to be looking at to begin with. So if you've got f prime equals 8x to the third, we have not been asked this before, but what is f of x? So we can think through this. We know that if we've got f prime, it's got to be one less power because we would have done the power rule to get here. And maybe you already thought of it really fast, but I'm just going to talk myself through it, that my f would have to have a fourth degree since its derivative is a third degree. And then I know to use the power rule and end up with an 8 here, that means that the coefficient had to have been a 2. So I had 2x to the fourth. If I were to take the derivative, I would end up with an 8x to the third. So we did it. We've got my original function would have to be this 2x to the fourth. But wait, what about if I add a 3 to it? Would I still end up with that same f prime? And I would, because anytime I take the derivative of constant, it's 0. So for that matter, f of x could be 2x to the fourth minus 287, and I would still end up with the same derivative because this did not matter. The only difference between these two is how the function is shifted up or down, and that doesn't affect how the slope operates. So I've got a lot of options. So what we end up with is multiple antiderivatives, where if I am taking the derivative of 2x to the fourth, I end up with this 8x to the third. But if my original function was 2x to the fourth plus 7, or 2x to the fourth minus 15, or 2x to the fourth minus 287, I'm going to end up with the same derivative. So there are actually multiple answers to this, which brings us to how we would represent what we call an indefinite integral. And that means that we are taking the integral of something and not ending up with an exact answer, but a family of answers. So first, a little bit of notation. If I'm starting with a derivative, so we've got our dy dx, our derivative of y with respect to x, equaling some f prime of x. And we are wanting to integrate. The notation that happens here is that we would actually move our dx to the other side, like we're multiplying it to both sides. And some of these things will feel a little bit weird today, especially notation, but remember that was the same for derivatives in the beginning, where we saw that dy dx, y prime, f prime, and there was a lot of notation there. This doesn't have as much variation in notation, but just getting used to it. Okay, so once I move it to the other side, how we integrate something or show that we're integrating something is this beautiful symbol. It's like a really tall S. This is an integral, an integration symbol, and it's saying that we are integrating both sides. And whenever I integrate dy, remember I am undoing, so I'm the opposite direction of a derivative. So if I have the derivative of y, that means that originally we just had y. So the derivative of y is dy, the integral of dy is just y. So hang with me here. If I'm taking the integral of f prime of x, this guy over here is notation. It's telling me that I'm taking the integral of f prime of x with respect to x. So this is kind of similar to whenever I would take a derivative and end up with dy dx. We found the derivative of y with respect to x. We're taking the integral with respect to x. So this guy is not an operation as much as it is just saying that's what we're doing. So whenever I take the integral of f prime, I would end up with what we started with, which would be f of x. And then because I don't know any other information to say it's this particular f of x, we're always going to have in an indefinite integral a plus c to say that whenever I integrate or I take the antiderivative, that I know this is the core of the function, but I could have some constant added to it or not, just like all of our options up here where there could have been a constant added to it to begin with. My derivative always ended up being an 8x cubed. So we know my derivative is f prime, but we don't know if there was a constant added or not. Okay, so some things that we've got going on here. This would be us taking an integral. We would call this part, so the part that we are actually taking the integral of, this is called the integrand, which is very similar to whenever you take the square root of something, you have the radical, and then what's underneath it is called the radicand. So this is the integral, and then underneath, or what we're taking the integral of, is the integrand. This guy is just called the constant. And we always use plus c, that is the variable that we use to add the constant. I've had classes in the past that want to give a name to c. I had a class that called it Carl. They had to add Carl. So if you want to come up with some way to remember that you have to add c when you're integrating indefinitely, then go for it. I have this picture of Carrie Underwood up here, and sometimes I forget why she's in this lesson, and then I remember that Carrie Underwood just wants us to undo it. So that is a song by Carrie Underwood. I'm sure that she was talking about indefinite integrals. So let's look at some basic integration rules to start with, and then we'll look at, for integrating just a polynomial in general, it has its own power rule, just like derivatives have a power rule where we're going to reverse differentiate. So starting with just, if we have an integral of 0, and remember this notation is going to say we're taking the integral of 0 with respect to x. And so if I'm integrating 0, think about the derivative that would give us 0, the original function. If we took a derivative, it had to be just a number to begin with. And so if I'm taking the integral of 0, it's just a constant. So just some c. Without more information, we don't know what constant. If we are integrating and we have a constant, so I'm going to use a different constant here, just some k integrating with respect to x, that means that our original was that's constant times x to begin with. So if we had like a line, then we would end up with just the slope as the derivative. And so when we integrate with respect to x, we'll end up with kx and then plus that c value, because we could have a constant that dropped off when we took the derivative. If we're integrating something raised to a power, so x to the n power, this is really the integral's power rule, that for a derivative I would multiply by the power and then take it down a power, and so I'm going to do the opposite to integrate. I will raise my power by 1, so I've got an x to the n plus 1, and then instead of multiplying by that, I will divide by it. So we'll raise it a power and divide by it, and this will become something that you are used to. It feel a little bit funny at first, but you will get used to going this direction as well, where, okay, we're raising the power and dividing by whatever that new power is. So if I had the integral of kx with respect to x, so k being a constant here, that I would raise x a power, so I would have kx squared and then divide by 2. Just like when we differentiate, that constant doesn't go anywhere, it's just chilling. So where normally I would multiply my power times the constant, now I'm dividing my new power in the original coefficient. C. And then just a few trig ones that we're comfortable with right now. If I'm integrating the sine of x with respect to x, oh sorry, I couldn't see. If I'm integrating sine, I will end up with a negative cosine. And for these, I think it's helpful to check because we're used to the other direction. So if I was taking the derivative of negative cosine, I would end up with negative sine, which is positive sine. If I'm integrating cosine, I will just end up with sine because the derivative of sine is cosine. So I always like to, especially at the beginning when we're not really used to it, go ahead and check by going the other direction because we're used to the derivatives more than we are the integrals. Okay, so some real numbers here. Go ahead and write this guy down. We are taking the integral of this 8x cubed minus 9x squared plus 4 with respect to x. Okay, so we will be using the integral power rule. I don't know if it has an official title, honestly, but it's its own power rule where we are raising each of these powers by 1 and then dividing by that. So we will have an 8x to the 4th divided by 4 minus our 9x cubed divided by 3 plus our 4 gets raised to power, so now it has an x, and then we always will have our plus a constant. And now we can simplify that our 8 can be divided by 4, our 9 can be divided by 3. This is not always true, but this one worked out nicely. Plus our c. So if you want to check, just like our trig functions, we can go backwards, that if I were to take the derivative from here, I would end up with my 8x cubed, my negative 9x squared, my 4, and then plus some constant that I don't know if it started with a constant or not, but ends up being 0, so we can't see it in the derivative. So this would be the integral, indefinite integral of that guy. So going backwards, it's like you're being given f prime and you're trying to figure out f. That's what we're doing. Okay, let's look at one more like that. Okay, go ahead and write this guy down. So in integration, there are not product or quotient rules. There is something called U substitution that we will use eventually, but we're not there yet. So anything that we are taking the integral of right now, you will be able to use that power rule, or it will be a trig function that you can go backwards from what we know the derivative to be. So before I get started on this, I'm not using any sort of quotient rule. So the first thing that I want to do is simplify by dividing each of these pieces by x to the 4th, just like we did with derivatives when we first learned the power rule. We want to take the path of least resistance, or the easiest path if at all possible. So my x squared divided by x to the 4th would be a 1 over x squared. I've got my 2x over x to the 4th, so if I canceled, I'd be end up with a 2 over x to the 3rd. And then I have a plus 3 over x to the 4th. So it's not looking great, but still same process that we used for derivatives. Before I use my integral power rule, I want to move everything to the numerator. So even though it will have a negative power, my x to the negative 2nd is 2x to the negative 3rd plus 3x to the negative 4th. That is what we want to do, because now we can go about raising each of those to a power and then dividing by it. Be careful here if you are raising x to the negative 2nd by 1, that means that you'll add 1 to that, and so we've got x to the negative first divided by negative 1. We'll have an x to the negative second divided by negative 2, and x to the negative 3 divided by negative 3. Oh, I'm sorry. We do not want that integral there. We took the integral. Sorry. We're integrating here, and now once we've integrated, we don't need that notation anymore. We do need a plus c. Just like whenever you take the square root of something or you take the limit of something, you don't need the notation after you have done the rules for that and taken the limit or taken the square root. Okay, so now in simplifying, if I can divide and simplify, which I've got a lot of that going on, I want to do that. And then if I have negative powers, it does make more sense for us to put them back in the denominator. So for this first one, we've got a negative 1 over just x. We can cancel here. We've got a negative 1 over x squared. And then a negative 1 over x cubed. So this one's a little bit harder to check, probably easier to check here than it is in our original function, but we are getting used to these a little bit more where we can say, okay, this would be a negative x to the negative first, so if I take the derivative, it would be a positive 1 over x squared. This guy would be a positive 2 over x to the third, and then a positive 3 when we multiply over x to the fourth. And then it could have had a constant, we don't know.